This next session is going to cover off what is, for me, one of the most exciting grants that the Zcash Community Grants Committee has made, and that is the one that they've made to Qedit to create Zcash Shielded Assets. This is going to bring user-defined assets, as I call them, or user-issued tokens, as other people have referred to it, to the Zcash blockchain. I think it's a key expansion of functionality for Zcash and a real step forward towards making Zcash a platform for commerce. So let me welcome Daniel Benarroch, who's Director of Research at Qedit, and Pablo Kogan, who's the Director of Engineering for this project.
Thank you.
Welcome, guys.
Thank you, Jeff. Hello, hello. Okay, can you all hear me well? Thank you so much, everyone, for joining. So I'm Daniel Benarroch, Director of Research at Qedit, and my co-speaker, Pablo Kogan, is the Director of Engineering. We'll do half-half, that's why he's not here with me right now, although he will be in a second. So thank you, Jack, for the introduction. As Jack said, we're going to be talking about the Zcash Shielded Assets, which we're now designing to be working on the orchard protocol. We haven't made this talk extremely technical, but also not like super high level, so somewhere in the middle. I hope most of you can follow. And if not, please feel free to write some questions on the Discord or reach out to us later on, and we'll be happy to discuss that. So the first thing we need to understand is sort of why ZSA, right? Why Zcash Shielded Asset? We have several reasons. I'm sure you all have many other reasons, but I think the main point we need to understand is sort of that it's going to enhance the functionality and programmability of the ecosystem, creating potentially a bigger developer community, right? This is something that Zcash has somewhat struggled potentially to reach out to because a lot of the development happens sort of at the core level of the protocol. Of course, at Qedit, we're happy to have joined or to be joining with this project. We want to expand the motivation of usage of the Zcash blockchain and ecosystem by introducing sort of a rich kind of token ecosystem and potential interoperability and really be like part of the rest of the blockchain and Web3 ecosystem. Not so much of a siloed system as Zcash has been, although there's been some interoperability work being done. We want Zcash to become a core component of privacy applications in the space. Sort of right now we can't compete with potential applications on smart contracts, for example, in Ethereum. But even then, there's some interesting applications happening at the privacy level that we would like to offer sort of maybe a higher degree of privacy because of the basic and core privacy in Zcash. Another reason is that now that we have a more stable proving system as Halo 2 that is potentially, hopefully, going to be standardized or is becoming the de facto standard, and the protocol orchard, which the core ECC team, Dara, Strat, Sean, many others have been working on and have made a huge successful progress there. It's really the perfect time to add multi-assets to Zcash, right? And really the final reason is just because we really all want it to happen, right? We all want to see this be done. So just a little bit about the actual project and the grant. So we're really happy and thankful for the grant committee for the opportunity and the Zcash Foundation. We got awarded around $1.2 million. So far, we've kind of completed 2 milestones. Also, thank you to some of the people that commented on those zips, which will, of course, be changing as we go forward to finalize them. The timeline is pushed a little bit as per the proposal, just because we started a couple of months later. And we're currently working in parallel in around like five different milestones. So we'll hopefully get to touch on some of these different milestones and update you. The team, again, is Pablo, Aurel, Vivek, John, and myself. So here, unfortunately, Aurel couldn't make it in the end, but he's with us in the spirit. Maybe he's watching, so hi, Aurel. Yeah, let's go for it. So actually, we are looking for teams to potentially audit this code because it's part of the sort of project commitment. We can help some team to get a grant and then work together on the audit because it's really important to do it. And although the Qedit team has audited Sapling and Orchard vanilla, we can't really audit our own code. So that would be great to have someone talk to us. So quickly, what are some of the design desiderata that we started this journey with? First of all, it was really important for us to sort of maintain backward compatibility with Zec nodes. We just didn't want to have another sort of turnstile situation or update of a protocol that would involve, de-shielding the assets and whatnot. And we really want to enjoy the kind of the previous anonymity pool that Orchard is offering from, the update that was a couple of months ago until we get ZSAs on mainnet. We also want to, of course, offer the highest level of privacy and protocol security, as has been the standard of the Zcash deployment. In this case, we are relating it to, of course, everything that has to do with the types of the assets and how much or no leakage of information around that is going to happen. And of course, make sure that our design is sort of in accordance with the security of the whole protocol as a whole, right? Which we know is a very difficult thing to gain. And actually, there I believe is going to talk about security of protocol design. So definitely interesting. Another important thing was that we wanted to minimize the circuit changes. Specifically, we wanted to keep the current size limit of the Orchard or the Halo 2 or the Orchard circuit in Halo 2, because that way we would not have to reproduce another time sort of the keys, and that it was also specifically related around not adding more hash functions that would add complexity to the prover. And of course, we want to keep in mind sort of future extensions of this protocol, because as a team, we're also hoping to continue providing, contributing to Zcash in terms of other applications. And actually, tomorrow we're going to be talking a little bit about this. We welcome you to join, discussing what can be built on top of ZSA. And of course, in the spirit of our Vegas convention trip, we want to say that what happens in the Orchard pool stays in the Orchard pool, right? So that's definitely important. Now, let's talk a little bit about high level of the components or the functionality that we're offering in ZSA, right? So now that we're introducing different types of assets, we need to start by having some type of issuance of assets, right? How do you create new assets on chain, right? So we decided to go for sort of a transparent type of issuance, because was important to track the total supply of the different currencies, whether they're wrapped assets from different chains or actual native assets that are sort of created for the first time on the Zcash chain. We want to issue, we actually allow with the design to issue many types of assets in a single transaction to many recipients, right? So this is a specific trait that we like, which is that at the moment of issuance, all the tokens can be allocated to all the owners of those assets, or they can be sort of allocated to some subset and then redistributed, right? As we will see in a second, the receivers are receiving like shielded notes, but actually, sorry, in a transparent way. So it's like this mix of things. So if you really wanted to be shielded, you need to resend it to yourself afterwards to completely untrack linkability. And finally, we have this idea of sort of finite or unlimited issuance, which is also going to be useful for key rotation, where basically if you're going to issue multiple times the same asset type, at any point of a new issuance, you can just flip that bit, and it will be de facto that type can never be issued again, right? And hence making it finite. In terms of the transfer of assets, it's sort of mostly the same functionality, and we actually made it so that if you're doing transfer of assets, it's almost indistinguishable from the Orchard vanilla. It's fully shielded, no type-related leakage or whatever. It's backward compatible, as we said, and really there is no consensus changes from Orchard, which is also important because touching consensus can be problematic at times. And then we have this third functionality that is this idea of burning of assets, right? Like we decided that we needed to add this because it's important for the whole bridging and interoperability. When you're wrapping assets, you need to unwrap them, and how do you do that? Of course, there's the usual sort of send it to a random address or the 0 address and whatnot. But there was actually some interesting extension of the transfer of asset design that allowed us to very elegantly sort of include a potential burning of assets that literally just burns the assets. Like they're not spendable even by random address or something. They are transparent, again, because you need to sort of match the issuance tracking of supply. And again, you can burn several types in one transfer and not all the value that you own. I mean, it's very flexible in that sense. And as I said, it enables bridging, right? Like the specific bridging kind of protocol or thing, we didn't actually get into that because we left it as a kind of more higher level implementation, right? If anybody's interested in implementing this, talk to us. We'll be happy to discuss. So a little bit more concretely, in terms of the issuance mechanism, we have sort of really four main components, right, for the issuance. So we have the issuer key and the issuer keys, which are ISK as the private key and IK as the public key. These are literally the same keys used and the same signature scheme used as for the spend authorization signature. We just created a kind of a new branch. Pablo's going to actually talk about it in a second. And together with the asset description, which we actually left it as a kind of a free form, sort of like a memo field in a way of 512 bytes, that can include any type of asset description. If you're using, I don't know, if you want to do NFTs or if you want to do some JSON object, there's a lot of flexibility there that can be, again, used for potential future applications. And when you put these two together, you actually create sort of the type of the asset, right? Like the asset description and the issuer ID hashed with the group hash creates the type. And as you see, the type is actually going to be a point in the curve, in the Palace curve, which are going to be included in the notes, right? So the note description, you can see it underneath. Before, it didn't have the actual type, but now it does, right? This is what's going to differentiate notes from Orchard or Zec from actual sort of custom asset. And then this finalization bit that, as I said, is sort of just a bit that you flip on and off to let the validators know, right, that it's the last transaction of that, the last issuance for that asset type. Of course, you need to sign everything using ISK. And in terms of the verification, this is something that we needed to implement. Well, you need to verify that IK verifies the signature. You need to check that the type is properly derived from the group hash, that all the nodes of that asset type have that type indeed. You need to check the finite issuance matter, whether it was already established as finite or not, right? Because if it was, then you cannot issue again. So that would be like a double issuance sort of problem. We haven't defined really the name of the different attacks. And then you need to really add all the values of the nodes, right? Because the nodes at this point are transparent, right? We don't actually publish the commitments. We publish the nodes in plain text. And then the verifier needs to actually derive the node commitments and add them to the Merkle tree of the Orchard pool, right? This is how you end up being able to use those nodes in a transfer later on, right, in a shielded transfer. So this is sort of the boundary point between the transparent part and the shielded part, right? Just briefly in terms of the issuance specification, as I said, the issuer ID is sort of this red Palace signature scheme, just similar to spend authorization. It's derived from the spending key just using a different counter and domain separator. And just, we don't use re-randomization because really it's not needed because everything's transparent anyway, right? And really the point is that you may actually need to have linkability of issuance instances because you want to make sure that the issuer is the same, right? Like that you can track it. I'm sure there is different ways, and if we ever wanted it, we could add the re-randomization methodology because it's there inherently. The asset description, as we said, it's sort of this free form. It could be used for bridging information, for NFTs, and as I said, if you ever find that your issuer key has been compromised, you can actually issue one final transaction with maybe a zero amount just in order to flip the bit and sort of define that asset cannot be issued again, right? And then just generate a new issuance key and publish to all your users that the new asset is going to be under this new type, right? And this is what creates the asset identifier, right? So the asset identifier, I didn't mention it before, but it's basically the concatenation of these two things. And this is sort of in the global state as a kind of a string that can be used for future protocol compatibility, because the type itself is actually the group hash, but the group hash using the Palace curve, right? So in that sense, you're already fixed to the Orchard protocol, whereas you want the type of the ID to be really compatible across time and protocols, right? So we hashed it concretely for now, but in the chain, it's going to stay in the global state as a kind of a global string that's in plain text, right? Or the pre-image of that hash. Sorry, all right, so for transfer mechanism, this is the basic Orchard transfer protocol in very high-level terms. Again, I don't want to get into the weeds of these, but if anybody has concrete questions, I think there is going to be a talk in this conference, and maybe not. If not, then come talk to us. Basically, there is this concept of node commitments that are used to hide and sort of commit, right, and bind the ownership of the different Zec tokens, right, the actual Zcash. The Merkle tree is used to store these commitments and in order to privately reference these commitments, right? Like when you create a transaction, you don't tell the validators, hey, this is my commitment. You tell them, hey, my commitment exists in this tree with this specific Merkle root. And also you tell them, well, and this is the nullifier that actually hasn't been published before, right? All of this is put together inside of the circuit, of the zero-knowledge circuit. And then you have this concept of dummy nodes, right? Dummy nodes are very interesting because it allows you to sort of hide the amount of real inputs and outputs that you're spending, right? So in order to match this pairing functionality in the transaction, because when you're spending, say, 5 Zec, you may want to send 2 Zec to someone and send yourself back 3, right? But then you have this dissonance of 1 input and 2 outputs and whatnot. We're going to see how we do this for ZSA. And then you have this very interesting sort of functionality that's using a commitment to the value of the node that is actually a commitment, a homomorphic commitment that is used then later to see that the value has been preserved between all the inputs and all the outputs, okay? So sorry for the really short and fast overview, but this leads us to sort of the main changes in the transfer functionality, right, for ZSA. First of all, the nodes are going to be typed. And of course, we want to preserve the type between the input and the output, right? Then we have that the node commitments, of course, include the types, actually accept the Zec nodes, right? So we're going to see how this is going to be used later for backward compatibility, but essentially the Zec nodes are going to stay the same even with ZSA, right? So they're going to have a default type without a type, right? This is kind of the idea. The value commitments, this is sort of the biggest change in the protocol. The value commitments, so the commitments to the value of the nodes, in the regular setting, actually have sort of the fixed base point, right? So if you think about a Pedersen commitment, I think I show it in the next one, so in the next slide, so I'll talk about it then. But basically, we're changing this base point that I'll show in a second. And then we introduce this idea of a split node, right? So a split node is the equivalent of a dummy node, except we just build it in a completely different way for non-Zec assets, right? And this is used in order to preserve the type of the output node as well. And we'll see it in a second as well. So for the value balance commitment, right, as I was saying, now we're replacing sort of, if you see on the top equation, that's the usual Zec value commitment where the value, the V net in the action is because you take the value of the output minus the value of the input, or the opposite. And you multiply it with this base point of the group, of the generator V orchard, right? And V orchard is essentially what we are now calling the type of the asset, right? So V orchard is going to stay as the Zec type, whereas for the custom assets, we're going to change that base point to be different things, so V type ZSA, right? And in this case, the verification itself is actually done basically in the same way because the balance is really preserved with respect to each asset. When you're going to take all the CV nets and add them up, the homomorphic operations are going to cancel out the values only with respect to the same base points, right? The base point for the RCV, so for the randomness of the Pedersen commitment, stays the same. That way you actually don't need to care too much about that. Okay, so I hope that was at least somewhat clear. In terms of security, again, this is inherent because of the security that already existed, right? Like it's simply because of the homomorphic property of the Pedersen commitment. So in terms of the transfer circuit, I will say a couple of things. Maybe Pablo will also mention a few other things in a second. So we essentially wanted to have a single sin semilla hash, just as the circuit of the vanilla orchard, because we don't want to increase the size too much, right? This is something we said in the beginning as a desiderata. And when you start having to differentiate between what you do with a Zec node and what you do with a non-Zec node, then you start thinking of, okay, how can you still have only one sin semilla hash or commitment while getting what you need, right, for both things. And essentially, for Zec, we do not add, right, this is computing, sorry, I should have said, this is for computing the node commitment, right, in the circuit. In the case of the Zec node, you, again, don't add a type to the commitment because, again, the commitment was already exists and you need backward compatibility. So you need to get exactly the same commitment as exists already inside of the pool, in the Merkle tree. Whereas for the commitment of new custom assets, you want to add the type because it's part of the node, right? So we take advantage of the sort of windowed nature of the sin semilla hash that allows us to sort of add an extra kind of round of computation of the hash at the end of the commitment. But there was a key point that we needed to note, and that's that for security reasons, actually, we needed to also change the domain separator because there is a different size of length in the input, and if you have different length size, then you may get some collisions. So we needed to change the domain separator. And for that, we used, so Aurel actually came up with this very interesting method to use a multiplexer based on the sort of is it Zec or is it non-Zec kind of bit input to the proof. Where at the beginning, it's going to choose what domain separator you're going to use, then compute the non-typed sin semilla hash, which when you go into the next multiplexer, if it's a Zec type, you're just going to output what you got, and if it's a non-Zec, you're going to add that extra round of the type, right? So we probably want to have some deeper review of the security for this, but at first sight, it seemed reasonable. In terms of the split node functionality, right? This is also important, mainly because, so let's look at the split node itself, right? Like in Orchard, you have this concept of action, right? And an action includes an input node and an output node. But again, let's say you're trying to spend some token of type A with, say, value 2, and you're going to have an output of value 1 and an output of value 0.5 and another 0.5, right? Like, it should be written output node 3, by the way. But in the regular Zec, you would have input nodes that are dummy nodes, right? But dummy nodes are completely created from scratch, and they have value 0 and so on and so on. But for the type to be preserved, you actually need to be able to reference it to some type or node of that type that exists in the pool previously. Specifically, right after issuance, right? Like if we're thinking about the loop, like the first instance of the node and the type on chain is the issuance transaction. And going forward, you actually need to reference that some node of that type that exists in order to be able to take the type with you to the next node, right? And so this is what we call a split node. In some sense, the split node is actually going to be a real node, okay? But we're going to sort of tweak the circuit so that whenever it identifies it as a split node with another flag, a split flag, it's going to zero out the value in the node commitment, and it's going to sort of create a kind of a random version of the nullifier, right? But it's going to prove that the commitment existed in the Merkle tree. Right? This is important because that way you're assured that the note is of a specific type derived from a group hash. It's a little bit more sort of convoluted than what I explained, but it was going to be too much to explain here. But there's some conversations in the different GitHub repositories. I welcome you to check them out. But note, keep in mind, sorry for the redundance, note that Zec nodes will maintain the dummy node process, okay? So again, for security, this needs more concrete review, but it really seemed like the split node functionality was properly designed. And just to kind of put it all together in terms of the backward compatibility, we have this kind of decision tree, right? Like where you have an input node to the circuit, and you look at the first flag if it's a Zec node, then you see if it's a spendable node or a dummy node, right? And you have the corresponding constraint checks in the circuit. And if you have a non-Zec node, meaning a custom asset, then again you look if it's a split node or a spendable node, and you do the corresponding things, right? Like this is for reference. There's details missing, so take it with a grain of salt. And just briefly to talk about the burn mechanism. So as we said, we designed it to be transparent, and we actually take advantage of this idea of, or this variable, this value called the value balance, right? If you've looked at the Zcash protocol before, you know that you can transfer assets from one pool to another, right? Specifically, you can transfer, say, from orchard to transparent, right? And how do you do that? Well, when you do this value commitment verification of the homomorphic Peterson commitment, you're going to either end up having like a net value of 0, in which case, great, you didn't take out any assets or input any assets to the pool, or you're going to have some balance that is going to be negative or positive, and that balance is going to be reflected in this value balance sort of variable that is essentially transparent, right? Now, we're taking advantage of this in the sense that for Zec assets, it's going to stay the same. You're going to be able to use it for either transferring to different pools or maybe to pay the fee, et cetera, et cetera. But for non-Zec assets, you cannot change it to different pools. The custom assets are not going to be defined in different pools or different protocols, only for Orchard. So we're taking advantage of that and using it in order to actually burn these assets. So if you see at the consensus level, it's going to be basically that if you see the value balance of a specific type, right? So now you're going to include the value and the actual type. You know that that type is burned, right? And the verification of the signature, the binding signature, is basically this extension, right? Like if before it was only the first line where you have the addition of all the CV nets for the homomorphic operation minus the value commitment with 0 randomness of the value balance of Zec, now you're also going to add or to, I guess, remove all the sum of the value balances that you're burning, right? And this, of course, should give you 0, and hence the verification key of the signature for verifying the Zcash of the binding signature. And finally, I want to talk a little bit about sort of the fees mechanism. I know this is a big, kind of important question. There was even like a survey that was created or a research report that was worked on by GMU and ECC on sort of economic incentives based on ZSA extension of Orchard. And we've been thinking that like at the end of the day, we want to keep Zec, maintain Zec as the core asset on Zcash. And in order to do that, of course, we first need to have that all fees will be paid in Zec, right? And sort of we thought about first 2 options that we could do for fees. One is where like basically as today the fees are proportional to the number of types or the number of recipients, specifically the size of the transaction, with a fixed fee, where basically all the bundles, so all the different components of the transaction are valued the same. Or we have another type of option which is more similar to what we see today in, say, Ethereum, where like each opcode has a different fee associated to it. And that's, of course, again, we keep Zec the basic fee denomination. But in this case, well, it could be fixed per transaction byte, which we believe is still like relevant and wouldn't remove any value from Zec. But now, for example, the issuance bundles or the burn operations may cost more or less, depending on what everybody agrees on, because maybe it's adding more content to the global state or things like this. And of course, if you have any other options, we're happy to discuss these. We definitely welcome the community feedback. Yeah, now I'm gonna let Pablo continue the conversation and show you a little bit of the implementation details that we've been working on. So thank you, Pablo.
So I'm going to show you some implementation details. I'm not going to go too deep, just enough to show you where things are headed. I chose this picture because in some sense, blockchains are similar to tattoos. Hard to deploy, hard to change, so we need to be extra careful when implementing those things. So let's get into it. For protocol changes, we have the orchard crate. It is very well written, and the code is clear, and we very enjoy working on it. So thank you, the Zcash team. We have our own fork. You can access it. You can see everything that I'm about to show here. It's not finalized, and it is subject to a debate and a review. We will finalize it down the road, but still the direction will be obvious. So first of all, we define a new set of keys, the issuer keys. We have a private issuance key and public issuance key. The idea is that you can delegate the issuance without revealing your secret key. Next, we replace the v-orchard base point. It used to be a fixed value. Now, to derive the value commitment, you need to pass the base point as a parameter. Each type has its own V base point. Okay, next, to derive the base point itself, we concatenate the issuer public key with the asset description. The asset description is a 512 byte array. It can be anything that you choose. It can be a hash for NFTs. It can be JSON. It can be name of the asset. It can be anything. Just concatenate them both together, hash them to curve. You will get your point. And this will be the node type. For the native token, for Zec, we do the same thing that we did up until today. We hash the fixed value, and we return it. And we use it as the node type for native assets. To bind the three slides together, now we can create the binding signature with ZSAs, without ZSAs, and we can verify this signature. We created a test. You can access it. It's working. It's in our repository. You can see it today. Next thing, nodes. So up until today, we had the recipient, value, row, and rseed. Now we add the type to the nodes. For node commitment, up until today, we hashed using the Sensimilia hash, but now we have more information. So for the ZSA node commitment, we're going to change the domain. This is because the property of the Sensimilia hash function that it is only collision resistant for fixed value. Since we add more information here, we need a different domain. And this is what we do, both here and inside the circuit. Next, for the node encryption, now we have, once again, we have more information. We need also to encrypt the node type. So our current proposal is to reduce the memo size for ZSA nodes from 512 bytes to 480, and then the size of the ciphertext will remain the same as it is today. This is the current proposal. Of course, we can keep the existing memo size, but then ZSA nodes will be distinguishable from from non-ZSA nodes. While if we reduce the memo size a bit, the ZSA nodes, the ciphertext will be indistinguishable from regular orchard nodes. This is open for debate, and we are waiting for feedback on this. Next, we changed the builder inside the orchard crate to add the split nodes. As Daniel explained, for every ZSA node, we have a split node which is exactly the same as the original node, just with the split flag on. So in the builder, we add those split nodes. Next, about issuance. So we created an issue action, which is inspired by the original orchard action. Inside the issuance action, you have the issuer key, the public key, the asset description, a vector of nodes, the finalization flag, and the signature. The idea here is that you can issue multiple nodes in one transaction and distribute them immediately. Think of an airdrop. You can say issue 1,000 nodes and airdrop them all in one transaction. Then we have the issuance bundle. Inside the issuance bundle, we have a vector of issuance actions. And this is to accumulate for a case when you want to issue an NFT collection, for example. So for NFT collection, you need a different asset description for every single NFT. So you create issue action for every single NFT, and you put them inside the issue actions vector. Everything together goes inside the issuance bundle, and this is published as a new type of bundle inside the transaction. Circuit changes, of course, all the changes also need to be done inside the circuit. This can be a subject of a talk on its own. The highlights here that the circuit need to accumulate for a node type, for the new value commitment, for split node, and to be backward compatible with the existing node commitment. Next, once the protocol changes are done, the real work begins. Also, we need to make all those changes inside the Zcash client. The changes that need to be done inside the client are, first of all, a new flow for issuance, completely new flow. Then we need to update consensus to check that the issuance is done correctly according to the rules, especially whether the assets were finalized or not. Then we have node management. Now we need to manage the node types inside the client, both for ZEC and non-ZEC nodes. And we need to make some RPC changes in a way that will be backward compatible, but still will allow this new ZSA functionality. So we mapped the changes for the RPC interface. We have one new command for issuance, issue token. We will have to change something like 20 existing RPC commands, but this will be done in a backward compatible way. And the rest, no change. So let's look at one example. Let's say Z-many, Z-send-many, the RPC command that is used for sending nodes. So we add new field called node type. The field will be optional. If you use it, you can transfer ZSA nodes. If you not specify the node type, the system will assume that you're trying to transfer native nodes. And it will work the same way it works today. Of course, when you're trying to transfer ZSA nodes, the privacy policy need to be full privacy, because this is only working with Orchard. This will not work with sapling, and this will not work with the unshielded nodes. So the privacy policy need to be full privacy. Otherwise, it will get rejected. Next, there are new fields when you try to view existing transactions. So we added the node type, both for spends and for recipient. Okay, next, the issue token command. If you want to issue a new token, you specify the account number, the description, whether you like to finalize or not, and then an array of objects, same as send many. You will get a result, the issuer key, the node type, and the operation ID, similar to other commands. And that's it. And we're open for questions.
Okay, thank you. Give me a second to bring up the Discord questions here. Okay. Have you considered allowing ephemeral asset IDs rather than requiring a registry with a defined issuer?
Can you repeat the question?
Yeah, ephemeral asset IDs?
Have you considered allowing ephemeral asset IDs rather than requiring a registry with a defined issuer?
The truth is that we haven't considered it. Like, it wasn't part of our thinking. Like, we definitely didn't want to have sort of a registry, like a name registry on chain. That's why we based the asset ID on sort of the asset description, like whatever the asset is about, and the specific issuer ID. I'm not sure how well it would work to have like repeated issuances, right? Like there would have to be some trust mechanism externally. I don't know. I mean, it's a really good question. Whoever asked it, I'm happy to discuss it.
Is the issuer key optional?
Well, to issue, no. But if you're not an issuer, you don't need to really deal with an issuer key.
The issuer key is transparent to the end user. You use the RPC command and you issue. Inside the protocol, it's derived and it is used. You don't have to use it by yourself.
Okay. This next question comes from someone who would like to see Zcash ZSAs used to compete with Aztec, where Zcash is like a shielded layer you can use to hold and interact with DeFi positions originating on other chains. Is this a kind of idea you are already thinking of?
Yeah, the answer is that we've been thinking about this. This is something that we're considering as a potential next project once we finish with ZSA. Of course, not very soon yet, but we're thinking about how to make it happen on Zcash. I mean, specifically, are we going to sort of wrap Zex and forward them to other chains, or are we going to also allow sort of the private version of DeFi on Zcash chain? I mean, there's different ways of doing that, and we still haven't figured out what's the best path.
Okay. Is it possible that some future version, including post-Orchard, might have a mechanism that would allow proportionate distribution of a fixed total issuance of a new shielded asset to all holders of any existing asset that's already in a shielded pool? So this sounds like a kind of an airdrop, or shielded private airdrop concept.
Yeah, it's complicated because you don't have access to the actual addresses of the users that you don't know, specifically for shielded pool, right? I don't even know if we know how many users there are in some sense. Like it's I don't know. I would need to think about it.
Probably the users will have to publish the addresses that they want to get the airdrop to.
Yeah.
Otherwise, this is the property of Zcash. Everything is shielded. This is the idea, right?
Is there a way to partly disclose metadata of a ZSA transaction while keeping the rest of the sender, recipient, or amount private?
Not the way we designed it, except for the burning mechanism. We really wanted to keep all the metadata and all the data completely private to the point that the transfer looks indistinguishable from the orchard transfer. But in the future, we are thinking a lot about applications that are a little bit more sort of on a global scale, and then you start thinking about how Zcash can interact with like governments and regulation. There, I would imagine that for certain specific triggers or events or transaction types, there could be some kind of metadata leakage, maybe to some viewing keys, right? I mean, that's why viewing keys were there in the first place, I guess. Stuff like this. We haven't made any specific property of like viewable or non-viewable for viewing keys, just as is, right? Like whatever you can decrypt on the ciphertext, you can see. So the whole note.
Of course, whoever transferred the note can publish the metadata, and then everyone else can check that this is indeed the real metadata using the note commitment.
Okay. I think this next question is asking you to peer into a crystal ball. What are the potential economic implications of ZSAs on ZEC?
There is a really interesting report. I recommend you read it by GMU. I'm not an economics expert, so I will refrain from taking too much of an opinion on that question.
How do you envision that price trackers and exchanges will track ZSAs in their website for users wanting to trade ZSAs?
Really, we envision it the same as it happens today. I mean, when there is a new token being issued on Ethereum, there's going to be some listings, some initial coin offering or whatever it's called today. And people are going to essentially end up tracking or believing, the listing ticker more than the actual sort of on-chain name, right? And that's why for us having Issuance be transparent for now was important, because that's sort of the first step into enabling custom assets under kind of privacy for transfer, but yeah.
Also, to trade, someone needs to create the system to trade the assets. So the operator can publish the transactions for everyone to see, right? This depends on the operator.
Have you talked to wallet or UX people about how to represent asset types to users?
We want to be talking to the wallet developers. Someone from the Zec wallet did reach out, so we'll be talking to them once we have more of the RPC commands all set up. But the idea, I think, is just to make sure that it's, first and foremost as usable as possible, right? Like, you don't want to have to track too many things as a user. You want the wallet to do as many things automatically as possible, right? Like, the design should be, in my opinion, better than MetaMask, right? Because we're dealing with like shielded stuff and whatnot. Just like today, the wallets don't tell you, how many notes you're spending or how much change you're getting and stuff like that. As the original sort of Bitcoin wallets would, you want the same type of functionality and usability.
What's the timeline for deploying ZSAs, and what do you need from other participants in the Zcash ecosystem?
Do you want to take that?
So Daniel mentioned the timeline, the expected timeline. Of course, this is a review pending and audit pending. So you can see the expected timeline at the beginning of the slides.
Maybe I'll differentiate, though, because the timeline that we committed to or proposed is actually for implementation of ZSA and at least agreement of the implementation and the design with the community and the core developers, whereas the deployment is, as we know, something that can take a lot of time even after the implementation of the protocol has been done. So we're really hoping to work together with the different teams to potentially build, I don't know if it's going to be NU6 or whatever the next update is. It's not clear yet, and I don't know if there is consensus yet on the core, at the core protocol level, like the developers, that this will entail a network update or just an update. But yeah, So we'll see, but hopefully not more than a year and a half, hopefully.
Cool. Well, that's it for questions from Discord. We're running a bit early, but I don't know if there's anything else you guys want to share with us, but otherwise we can finish it up a little bit early.
Yeah, just to say that we're really happy to be joining sort of the developer team, the core developers, to build the protocol of Zcash and what we want the future of Zcash to be. Our expertise is really on the applications level and building all these applications in kind of in a usable way and private. We welcome any collaborations. We want more developer teams and experts to be working on Zcash because that's what we want for the currency for the future. So yeah, talk to us. Thank you.
All right, thank you very much, guys.